Now I'm recording. Yeah, thank you. I really appreciate by your comments. Now today I will try to put more attention on the comments. But as I said, we are starting with a simple equation here just to show that the theoretical things about pins are possible. So this is really interesting because I've been contacting by people saying, okay, pins are really good theoretically speaking, but when we have real problems in the world, problems like data sets and this kind of thing, real data, how can we put this as a really useful thing? We are talking about theoretical things, but how can we put this on the practice? How can we put this on the real world? And I think that these classes, these lessons are the best way to do this because, as I said before, we are not sure yet about which architecture to use for pins, which way to solve the problem. We don't have a recipe for doing this. But talking more about this, discussing more about this, I think that this is the best way to reach this goal in the future. Uh, but all right, just remembering what we talked about on the last classes. Uh, the physics informed neural networks concepts are the like we have a neural network which can be any kind of architecture. There are some papers using MLPs. There are some papers using LSTMs. There are some papers using neural operators. So the architecture itself is not what build a pin, but the concept behind a pin is that you can approximate the function, the values of the data, not only by comparing the data itself, but also comparing the physics concept itself. So how can we do this? We embedding the loss function inside the physics concept, the physics equations inside of the loss function. So here we are starting again as a 1D hit equation. I'm using 10,000 collocation points for the data set and 100 points in the initial condition and the boundary conditions for this equation. So for this equation, we have the initial conditions as the hit in x and 0, it's the scene of px, and the boundary condition is like the for 0, the x, 0 and t, we have 1 and t, and all of the points are equal to 0. So when we start using the pin concept here, the first thing that we have for the code is to import here with the first example we are using PyTorch. So we are importing the torch module and the neural network module from PyTorch, and also the NumPy with the alias as NumPy. Here we are using for just a theoretical example, the alpha set it, fix it as 0.01. I forgot the name in English of the number, but yeah. Here is how we build the neural network, and this way to building the neural networks, something that we saw a lot on the Raisi papers. We do a loop of iteration by the number of layers, then we create like a sequential neural network, simple one using the number of layers. So we set an array of the layers that we are using in the neural network, then we just append the linear conditions for the neural network. So it's a simple linear and it's a simple recurrent neural network. So it's MLP here. The main point for building this is that we can use the torch autograd functions for calculating the differential parameters inside of this. So instead of using the NumPy or any kind of way to calculating the gradients here, we are using the PyTorch, and we will use the TensorFlow autograd functions here to calculate this. So here is the way we calculate the derivatives of the u by x for each order of the function here, the PDE here that we are calculating. So I won't run this again because this took a little bit, but I've already run this before, so I will show just the results. So how many collocation points do we need to take for, yeah, this is a great question. Just let me check here. Mr. Biswanath Barman asked sir, how many collocation points do we need to take for a particular problem? How can we ensure that? This is a really good question, because depending of problems, when I saw about the race papers, we had some different collocation points. So depending of the complexity of the problem, we need to put more. But we don't have like a number exact, but we need to ensure that we are not overfitting the neural network, but at the same time we need to ensure that the training will converge in some point. So we need to test different collocation points and always check the loss functions, the loss values. One important thing that is that we can print and we can check the different kind of loss values on the function. So we can have the loss of the data, we can have the loss of the initial conditions, the loss of the boundary conditions, and the loss of the equation itself. Then we can compare, okay, if we use 10,000 collocation points, the neural network seems to be learning with the data, but increasing the collocation points computation, yeah, exactly. Increasing the collocation points, computational costs also increased, exactly. It's like the trade-off problem. We need to put the number of points that will allow the neural network to understanding the problem, the physics concepts, but at the same time we don't want to put infinite numbers to have like a overflow of memory. Alexei Boyko, how we can ensure that nothing weird happens between the collocation points, okay? Can we somehow control it, or we just imply that since we fit gradients and second derivatives, our function will be smooth enough for the solution not to give random noise in between of the collocation points? Yeah, this is a really tricky thing. Sometimes I had some problems training pins. I was just checking the initial conditions and the boundary conditions, and then I get the loss functions, and I was like, okay, the loss is decreasing, so probably the neural network it's learning. Then when we plot the data at the end of the training, I saw some weird things like probably the initial conditions or the boundary conditions that I set it are not correct. So this is a problem that we have with pins, and I had a way to try to solve this that I will show in the end of the presentation. But one thing that for me generates lots of problems with pins is that we depending not only the collocation points but the initial and boundary conditions points. So sometimes we had problems with the boundary and initial loss the cost function for the initial and boundary conditions. So it's like the neural network is learning with the equation, but it didn't obey too much about the boundary of the equations. So it's not a silly thing. I don't have the answer for this. I think we need to study more for getting the best way to solve this. But this is a really good thing to getting this to getting those questions. This shows for me and for all the people that pins are not the holy grail for solving physics AI problems, but I think they are starting this. So we have a problem with sometimes we didn't converge, increasing the collocation points, and also we don't set correctly the collocation points. The best thing that we can do is to apply the correct physics conditions and try to reach the convergence, because mathematically speaking we are doing the best thing for this. Okay, so here we set the gradients. Yeah, someone's trying to do it. Okay, so here we have in the training points, we have set it 10,000 points here, 100 for the initial and boundary conditions. Then we put here the gradient. We put the requires gradient as true because we will derivative those two functions here, those two results here, those two matrices. So here we calculate the x and the t values. We set initial points here for the x and the t. Then we set the initial points for x and t. and do the same thing for the boundary conditions. So we are just obeying the conditions we set in the beginning, and we generate the collocation points here, as we said it before. Then we use this for training the data. One thing that is important is like for this example, we are not separating training tests and okay, my energy here died, but okay. We are not separating training tests and validation data set, but this is speaking about data science training of machine learning, physics informed neural networks. This is a really important thing to do. So one thing that it's a good tip for training neural networks using pins, we can use like suball functions for generating the collocation points. It's one thing that we can use to guarantee that we have more security in the results. So after generating the training points here, we start the training, just get the training points here, we put the requires gradient as true because we will derivative some points. Then we start learning here for we allow the neural network to learn here. Then this is the point that I was saying. If we are training just a neural network, recurrent neural network, we just start the gradients here. Then we get the loss of the data itself, like could be a mean square error, for example, for the data and the predicted results here. But here we have the loss for PDEs, like we get the initial points, we get the prediction of the model, then we compare with the real gradients here. So we do this for the PDE, we do this for the IC, and we do this for the BC. Then we summarize all of the points, all of the loss, and we pass this to the model. So in this kind of architecture here, in this kind of training here, we are just passing and teaching the... Okay, we have some... Elias share some papers. Yeah, Bisvana, take a look at these papers. Thank you, Elias. So we are adding the different kind of loss functions here, the PDE, the IC, and the BC, and then this will be the loss function of the neural network. So in this training here, we are not adding the data loss function here. We are just adding the physics loss function because we are trying to explain the main concepts behind physics informed neural networks. So when we do this, we are saying the neural network like, okay, you are trying to optimize the difference between the real value of the PDE, the real value of the initial conditions, and the real values of the boundary conditions. Then we'll try to optimize this difference between the predictions of the model. So the model will try to obey all of those conditions. So we are not just training with the data, but we are training with the physics conditions here. One thing that is really interesting looking at this, because when I started studying pins, we have the physics name in the beginning, like physics informed neural networks. But if we analyze here, it's like we can add different kind of nature behaviors inside of our neural network. So imagine we have a different kind of problem from a different kind of nature, and we have like any kind of mathematical behavior here. We can add this inside of the training, like in this part of the loss training function. So the main concepts when we will talk in the future about the physics informed neural operators is like we have the physics operators, like imagine Fourier transformation or Hilbert-Hahn transformation. We have this, we can embedding these same concepts on this part of training here. So it's like we add a transformation in the data inside of the training. And this is really interesting because we are talking about physics informed neural network because we are applying physics concepts, but we can open more the mind, like we can add different kind of constraints inside of the training of the neural network. We are not just, it's like we don't need to just thinking about the nature equations, the physics equations, but we can talk about everything that we have patterns we can add here. So this is an interesting theoretical thing, but makes me think more deeper about the problem. Here is how we create the neural network using the class, the PyTorch class that we set. So we have two neurons and like two features in the beginning of the training. Then we have one output, and we have three hidden layers with 64 neurons. So this is the way we are doing the neural network. Sorry, the architecture here. And here we train the neural network. So one thing that is interesting when I've just set like 5,000 points of training. And one thing that is interesting is like we saw a decreasing of the loss, but we saw like instability here. Like the loss is decreasing, then increase, then decrease, then increase. It's like we don't have a exponential decreasing of the loss function here. The convergence is not smooth as an usual neural network, and this is probably because of the architecture. And this is probably again one field that we need to study more. How can we improve the architectures of the neural networks? How can of the physics-informed neural networks to reach this convergence and reduce the time for training? So I will read the comments again. Sir, I'm curious about the training set and validation set in physics-informed neural networks. Are we only validating physics, or are there other aspects to consider? In traditional supervised machine learning, the training and validation sets are crucial. I would like to understand these concepts better. Just for curiosity, I asked this question. This is amazing, Bisvanat. This is an amazing question because right now in physics-informed neural networks, we had a problem. We have a problem, and this is why we think more theoretically about this field, because the main papers, the main researches, the main core things that we have in physics-informed neural networks, we use simulate data sets for the experiments. So we are not using real data too much. So we are validating the physics concepts, and we add the data set inside of the training. But we are not like so sure that we have this for real in the real problems, because we are not doing too much research using the real problems. And I think that this is how probably we can reach the huge potential of the physics AI field. When we put the real data united with those physics AI concepts, we have probably we will have probably the best results and the best application. So right now it's a problem we have, because the main part of the researches came from simulating data sets. But there are some companies and there are some people, like I'm trying to do this for like taking some real simulating data. When I say real simulating data, it's like the ANSYS, the console simulators. We took that data from the training, and we put this for like the neural network. So we use real data. It's simulated, but it's really closer to the real things, and we try to optimize that. And the one question that came from this is like, why we are training a neural network to do the same thing that a simulator does. And one thing is like the time for generating the simulations is really high. So for changing a single parameter in the simulation, we probably took like hours, days. So it's not something really scalable. But we are sure that those results are really accurate, because we are using these for like centuries, I would say, in engineering and this kind of thing. So we should probably took those results that are really accurate and try to do a way for getting the convergence and generating the simulations more faster and really accurate as the simulator. So probably this will be the future. We took the simulators results, and we have some examples I can share in another call more examples like this. There are some companies doing this, like the Goodell AI, some guys like the Azarac. It's another company that is trying to do this. But this is like the people are starting to take a more deeper look at this, and this is really important because when we use the real data, we are really doing the real problems because we will face a lot of difficulties, but this is the way that should be. It's not like only using the simulating data set. So this is a really good question, and it's a really good point and important. And again, I'm saying this again because physics informed neural networks, as I say, is not the holy grail in the physics AI, but it's a way to start looking more deeper about this. How can we embed in physics concepts? How can we put more trustness, and how can we put more accuracy and speed in the simulating data and all of those processes? So this is the main like strengthness in physics informed neural networks, and this is also one of the difficulties and the challenge that we will face. So again, amazing question, amazing. Here I've put an example using TensorFlow, so it's really similar to the other one using the PyTorch, but we are not using the PyTorch here. So the way we are using for create the neural network, we put the keras from TensorFlow, then we use dense layers inside, so it's really similar. The architecture, sorry, the architecture will be similar, but the way we solve this is just putting a different kind of shirt here, but it's the same thing. But one thing that I would like to show you is like when we talk about PyTorch, we had the outgrad function here for doing the differentiation here. So we have the outgrad here using PyTorch. And when we use TensorFlow, the main point here is like we have the gradient tape here, and this is really useful also for training neural networks, especially when we use physics informed neural networks. So the way we do this, we call the gradient tape here from the TensorFlow, then we calculate the gradients here. So we can do this, we get the UX and UT, and we can do this again for the UXX. So this is how we calculate the results here. We call this as a function called get residual. Then the training is the same thing. We start the training functions. We get the collocation points here. Then we calculate the loss here from the residual. So we calculate the residuals here, which will be the equation itself. Then we calculate the loss function. Then we also calculate the initial conditions and the boundary conditions loss. So it's the same structure we have here, and we do this optimizing this, applying the gradients here in the TensorFlow. So it's the same way we are doing. As you can see, the architecture we are using is the same we use for TensorFlow, is the same for the PyTorch, and this is the results I had here for this silly example using the TensorFlow. So let me check again. Thanks, David. Nice to see you. I will record this meeting, and then you can share later. Okay, so right now we just started the main concepts about understanding the physics informed neural networks training. We talk about how can we use the PyTorch. We talk about how can we use TensorFlow. But the main concepts here is how can we train a physics informed neural networks, because people talk a lot with me about how can I train and build my own physics informed neural networks. And I think that this is the thing that we need to understand. We will have some difficulties, we will have some problems, like as you ask, like how many collocation points, how can we ensure the collocation points. Those are problems that we will need to face to understanding the training of physics informed neural networks. So when we go to the practice, I think that the best way to learn is to going by ourselves and trying to understand. So now we have the main concept, like, okay, I have to build a neural network and I have to put the loss functions inside of the training. That could be the initial conditions, the boundary conditions, the the equations that we have. So we have the behavior, the physics behavior inside of the training of the neural network. This is the main concept. And I will also add another important thing that sometimes, sometimes not, but all the times we need to ensure that I forget the name, but we need to ensure that the dimensions of our data it's the same. So we don't want to have like an x that comes from 0 to 100 and a t that comes from 0 to 1. So we need to normalize the data set. This is the word that I was trying to understand. So, okay. So the main concepts that we have for data science training of neural networks, like supervised training, we need to do the same thing here. So we need to split the data sets. We need to take care of our data. So we need to ensure that we don't have any kind of not a number values there. We don't have any kind of infinite values inside of this. One thing that happens a lot when we train neural networks, physics from neural networks, is that sometimes the gradient, when we do this from complex equations, the gradient explodes. So sometimes we have the loss functions and then we just appear like infinite, infinite, infinite. This is a warning thing. When we solve this, probably the results of the derivatives are going to exploding. So they are too higher and the computation is not being able to do this. So this is one thing that happens a lot when training physics-informed neural networks. The gradients can explode, and the TensorFlow gradient tapes try to solve this a little bit. So this doesn't exactly solve all of the problems with the exploding gradients training, but it's something. This is one thing that can try to help a little bit with this. So going for the physics-informed neural operators, we have the Pinot concepts here. When I talked to you at the beginning, we have like a neural network. We put the equations inside of this, and we have the initial conditions and the boundary conditions inside of this. The main concept about physics-informed neural operators is like we have the parameters of the equation itself. It's not the equation, but the physics concepts, the physics behavior. Like I've talked a little bit about Fourier transformation. So sometimes we can apply Fourier, fast Fourier transform for some time series forecasting data. Then we get the frequencies and the dampings of the wave that we generate. So we can use those parameters, those operators, the frequency and the damping values. We can use these for generating like periodic functions like sines and cosines. They are not exactly the main equation of the field, but they represent the behavior of this field. So we use this a lot in physics. We math engineers. So this is the main concept of neural operators. We are not trying to find the equation itself. We are not trying to represent the behavior of some experiment by the equation itself, but we are trying to approximate using operators, mathematical operators that can do this. So I've talked about Fourier transformation, but here I got a simple example. We generate a data set for a damp harmonic oscillator. So we have the here we have here is an example of the data that we have. We have a damped harmonic oscillator. So we have this behavior. The true signal here is the value itself. So we are trying to approximate these values using physics-informed neural operators. And when I talk this, is because damped harmonic oscillators, we have the values of the frequencies here, and we also have the damping values here. So this is the way we are representing this function using a mix of cosines and sines here inside of the function. So we do this, and we generate the data set here. We just allow some more people. Yeah, okay, so this is the plot of the data. And how can we train these physics-informed neural networks? We start the data set here. We put the number of samples that we'll have. Then we get the values of the frequencies, and we get the values of the dumping values here. So we have the parameters of the neural network that will be approximated. That will be, in this case, the parameters of this function here. So we are trying to approximate the main concept here for neural physics-informed neural operators, like we are trying to approximate a mathematical function that is not exactly the physics function here. So the way we train this is really similar to the other one, but we are not using the physics equation itself. So when we have the layers of the neural network here, I'm using a MLP function, MLP architecture. Then in the forward here, we have the context that will be the operators calculating here. So we do this, and the results of this neural network, I don't know if I run this. Yeah, I run this. So this is the loss functions for training and validation, and this is the results we have. One thing that is important is like when we get the results here, the predictions for physics-informed neural operators, the results of the neural network will need to be summarized by the parameters that we have. So we need like to estimate the period and the amplitude of the wave that we are calculating. Then we add this to the result of the prediction here. So when we do this, we get like here some. Yeah, this is the results that we got for these physics-informed neural operators modeling here. But the main concepts, like we are not applying the physics equation itself, but we are applying the the operators calculation itself. I try to run a little bit because probably I will have just more 30 minutes in the meeting, and I have some more things to go with this. But this notebook will be shared with you again to you for trying to do by yourself and studying more about this. I have more questions on the chat. Andrew Bedwell, input passes through this multi-activation functions means no discontinuity found. So in what case we might face exploding gradients? And yeah, this is a good question. Sometimes we have some weird behaviors when the neural networks like gets an error. So imagine that we start with a simple error, then we keep training the neural network. We have the limits of the limits of the functions, but then the neural network predicts someone that is really above of the limits. We will try to get the error, and we'll try to optimize the error, but sometimes when we get one starting error, we increase I forgot the name in English, but we spread this error for the rest of the training. So it's like we have a silly error, then we increase the error, then we explode the error for doing this. It's like the neural network is wrong sometimes, then it start to be more wrong, and then the error explodes. So it's not a problem exactly with the collocation points, but it's a problem with the parameters that the neural network is trying to use for approximating this. So this sometimes happens a lot, not only with physics-informed neural networks, but with neural networks in general. So yeah, another thing that I've prepared here was using the DeepXDA. That is a framework really used. Let me try to put it. I will share with you DeepXDA. So till now we are just using the TensorFlow and then PyTorch for training the neural networks. We go for physics-informed neural networks, we go for the physics-informed neural operators. So here we start going more deeper in some frameworks that we have. So the DeepXDE, it's a framework that is really people use a lot for solving physics-informed neural networks. They have some included concepts inside of this, so you can set the backend that you will use for training the neural network. You can use JAX, you can use PyTorch, you can use TensorFlow, and also Paddle. So it's embedding inside of the package, the DeepXDE package, and the main the best things inside of this framework is that you can add and set your geometry. I would say really easily, but it's not really easily because I had some troubles using DeepXDE. But you have some functions for geometry, 1D, 2D, 3D using DeepXDE. You have ways to setting the boundary conditions, initial conditions. So you have you can create like Dirichlet conditions easily using this. Yeah, I think this is the main concepts about understanding the framework, the DeepXDE. If someone used this before, just let me know. I didn't use too much DeepXDE, so I just bring an example here for showing you guys the way we can use DeepXDE. So we are importing the DeepXDE. We put the DDE here as alias. Here I set the TensorFlow as backend. I was using the global initialization for this example. You can check more here after the call. Then I just install I need to install again the package, and this is probably one thing that made me not using too much about DeepXDE. Is for me is not really stable. I had some problems with versions, Python versions. When I tried to use for Google Colab, I had a lot of problems using DeepXDE. So, but probably it's a thing that with me, and I didn't use too much about DeepXDE, but I wouldn't say it's a bad framework. Probably it's really good, and I'm not just using the best way it can. But here I'm importing the packages again. I'm setting the equation, the PDE equation here. We generate we use the gradients, we calculate the Hessian matrix here, we put the t and the x, then we do again for calculating the other derivatives. So, sorry. And this is how we set the boundary conditions here. So I just set it by manually here, but we have some ways to do this. Yeah, it's here where I was trying to find. So after setting the PDE here using the DDE grad, we can set the geometry. It is really simple, like we have geometry. I'm using a simple rectangle here that comes from 0 to 1 in x and y. Then we have the boundary conditions. I've used the Dirichlet boundary conditions here. Then we put the geometry. It's a rectangle, so we have 4 boundary conditions, like the 4 points of the edge points of the rectangle. So then we generate the data using the, yeah, just let me check. Yeah, all right, we have, in DeepXDE, sir, I have to face a defined boundary condition and take back in TensorFlow and PyTorch. Amazing, Ms. Vanat. Feel free to talk more about this. I didn't use a lot of the DeepXDE, but I think this is seems to be a really good package that I need to go more deeper. Guys, we will have like 12 minutes here in the call, but I will create a new link and then we can go there, because probably I will spend more than 12 minutes here. Just let me create a new link. Okay, I will share on the chat the new link for the meeting. Please go there, because here we will have less minutes. Okay, just add people here. I will share my screen again. Just a second, guys. I'm accepting people for the meeting. And thank you so much for being here. When I start doing those calls, those classes, I wasn't expecting this to have so many people here. So I'm really happy for the results. This is, yeah, I wasn't expecting that people would like to learn about physics AI. So this is really amazing for me. And I think this is the best way we can do for talking more about this field. So yeah, people are still entering. All right, so keep going here. We set we create the data for the thank you, Devo Present. Here we set the data on the for the dpxde function here. We pass the geometry, we pass the equation that we create, like the function that we create. We have the boundary, the initial, we have the boundary conditions here set it. Then the number of the points for domain and the boundary conditions. So just let me check. Okay. Then we create this object, this data object. Then we create a neural network. Here is really easy how we can do this using the dpxde. We put the neural network, it's a forward neural network. We have two inputs like features. We have two features here in the beginning. Then we have four hidden layers with 40 parameters inside of this. Then we have one output. Then we use hyperbolic tangent as the activation function, and then we use the way we generate the data sets global uniform. So this is how we create the model using the dpxde, and how we compile and train the neural network model. So this is how the outputs should be, like the dpxde. And this was my trying to put this for you, but feel free to use more and give me some feedbacks using this, because as I said, I didn't use too much about this package. Just let me check if there's someone trying to get into the call. Probably, yeah, I think it is. All right, so keep going for the last parts of this meeting. I was trying to put some physics Nemo examples here, but I think that it's better for this call to just show the package itself, because I didn't use again too much, and the results that I get on the notebook are not really good. Not the results, but the way to explain and teaching this. So I don't think it's a good way to go there. But the physics Nemo, it's the modulus from NVIDIA. It used to be NVIDIA modulus when I started studying this, but now we have the physics Nemo. Then you can check the package inside of this. It's from NVIDIA. You have some great stuff here. Then yes, the way we can use this. I was trying to use by Google Colab, but I had some difficulties. Let me share the screen again. Yeah, and this is the GitHub repository for the physics Nemo. Here we have some examples. When, for example, I was trying to see this, we have CFD, then we have, for example, I took their C, Fourier neural operators here. So we have Fourier neural operators for the C flow. We have this Cody train Fourier neural operators. So let me check. Okay, here, train Fourier neural operators. So probably if I try to run this on my Python will run, but when I try on Colab it didn't work. So yeah, probably I need to go more deeper into this. But as I saw, the Physics Nemo from NVIDIA, they have some architectures preset there, like some objects, like we have Fourier neural operators here. We just call the Fourier neural operators. We have the input channels, we have the output channels, the coder layer. We pass this in as an object for loading this. So we have this like a config object, and we pass this config object inside of the Darcy trainer here. So it's a dictionary with the configurators that we have for the training. So for this, we just load the model for the NVIDIA Physics Nemo. Then we do the training as usual. But the main thing here is like we have in this package some presetted architectures and models. So this is the best thing that we can check here. Inside of Physics Nemo, we have models, for example. Then we have here some solving models. We have like a simple MLP, so we have a fully connected model. We can load this and try to test in different kind of ways. This is probably the best way that we can use for training and practice using Physics Nemo. Another package that now that now reminds me using this is the let me remind the name. It's IBM. Forgot the name. Physics formula. Forgot the name of this. It's a package from IBM that, yes, simulate. Here, this package from IBM. The guy that built this, it's a great friend of mine, and he showed me about this. This is really cool because it's really similar to what the Physics Nemo has. We have inside of this some models presetted here where we can use like we have, for example, optimization, regression. Yeah, we have extreme learning machine models here. We have operator inference models here. This is a really cool framework for using. Also, we have different kind of models, and I really encourage you for exploring this package either. Yeah. So going back to the notebook, I tried to put an example using the Physics Nemo, but for me it's not really it's not what I was trying to show you, but this is how we can use. We are using the parallel training for the PyTorch. Then we load the distribute manager for the Physics Nemo. Then we load a simple fully connected neural network here, just to showing how we can use this. Then we create the architecture here. We put the fully connected. We have the input features, 32. We have the 64 output features. Then we do this. Yeah, it's like we do the training here. We have the distribute parallel. We have the device IDs, output device. We set the parameters here. We load the optimizer. And then we have the training step, like we do the prediction, we do the loss. So it's like training a simple neural network. But the main concept here is like we can load the architectures inside of this package, inside of this Physics Nemo package. So it's a really useful thing. We can explore more. I will go more deeper into these fields. Just let me check the chat if you have Okay, nothing. Okay. Yeah. So for the last part of this meeting, I've prepared two more examples. One is for the PL, Physics for Extreme Learning Machine, and before going into the the code itself, I will share the paper that generates this idea from Physics informed Extreme Learning Machine. The extreme learning machine theory comes from this paper here. Paper. Let me find. Yeah, the extreme learning machine theory comes from Professor Guangbin Huan, which delves into starting a training of a neural network using random weights and bias in the input layer. Then we fix this as random parameters, and we just set this as fixed in the beginning. So we put this in this paper. People use the Vikas Dwivedi use the extreme learning machine theory inside of physics informed neural networks. So here I had a silly example about how we can use this. We are loading the NumPy and AutoGrad functions here, and I put the matplotlib for plotting the results. I'm just loading activation function, the sigmoid here. We have the input dimensions, the hidden neurons, and then we start the random weights and bias for the beginning of the training, as I said in the theory of extreme learning machine. Then we have the hidden layer output, where we calculate, we have the dot value of the weights and the value, the variables. So it's like the main concept of the linear algebra for a neural network. But the main concept here is like, after doing this, we calculate the pseudo inverse of the function. So this is the theory behind physics informed extreme learning machine. So we here we are doing the calculations. Then we have the pseudo inverse here. Let me check. Okay, here we have the pseudo inverse here of the matrix. Then this is how we get the results here. I'm trying to go faster because I don't want to extend too much, but this is a really useful theory for solving physics informed neural networks problem, the physics informed extreme learning machine. And also I had another example that is the best thing for me here. It's like someone asked me about the if we have different kind of behaviors in the same function. So I won't go further of this because I probably extend too much about the meeting, but we have another concepts that I will share just the papers here. I think it's the best thing for you. So you can share the XTFC, Extreme Theory of Functional Connections. It's a paper from Enrico Chiasi, Carl Lake, Mario De Florio. This is an amazing method for solving physics informed neural networks, because we approximate some functions. We don't need here to put the boundary and initial conditions for solving the problem. So this is an amazing way to solving this. By the time I won't go further on this, but I really encourage you for understanding more about these concepts, because here we don't have the dependency of using the boundary and initial conditions. We have the equation, we have an approximation, and this is an amazing example of the power of the XTFC result. So this is really cool. I will do another call, another meeting for talking more about those specific examples, because I wasn't sharing the screen. Sorry guys. Here we have the results of the XTFC model that I was trying to show you here. Probably I will need to do another call for explaining more about those two concepts. They are not so simple for understanding, but they are really, really, really powerful. And the time for generating the results are really, really faster. So this is a little bit about the field of physics-informed neural networks. How can we understanding more about the practice? But I think that we are starting to build some knowledge field for going and developing more things in the future. Before, yeah, I will just let me check if the let me check his name. Someone was wanted to share a presentation here. Let me check. Yeah, let me check his name. Yeah, it's Gushram Singh. I don't know if you are here in the call, in the meeting, Gushram. Check. Yep, I think he's not here, but yeah, okay. If you are here, please let me know. Then I will allow you to share your screen and talk more about your work, your research. But while I will share the Discord link for the channel that we have for the uh, physics AI field. We I've developed a Discord channel for talking more about physics AI. It's called Pineapple, and we are trying to do some researches for. Yeah, here is the Discord channel, the Pineapple Discord channel. The bots are not running yet. I need to. But here in our Discord channel, you can we have some bots where you can try to find some papers based in some uh, terms. So like here, papers, docking program, benchmark. Then we have some papers for this. All of those things are open source, so we are not doing anything from yeah. All of the resources are open source, so we can do this for papers. We can do this for repositories on GitHub. We have some reference in our Discord channel. We have some discussions about physics AI in general. So feel free to get into the channel. I think would be amazing for talking more about physics AI field. I think this is the best way that I truly believe it's educating. It's talking more about this field. So I will share on the screen, on the chat, sorry, the link for Discord channel. Feel free to get into there. Feel free to add me on LinkedIn also. I share some yeah, I share some things about physics AI there. And yeah, I think the main goal here with my work is to spread this knowledge about physics AI. I think this the only thing, the only way that we can reach those dreaming results with physics informed neural networks in some years in the future. So thank you all of the people for coming here. It was really really amazing for talking more about this field. I'm really happy to for doing this, and I hope to see you on another meeting. Thank you so much. I will stop this screen, the call here, and we'll share with you. Thank you, Mario.